This video is about temperature and thermal energy. By the end of this video, you should understand the difference between temperature and thermal energy. You should be able to differentiate between system and surroundings. And you should be able to differentiate between endothermic and exothermic processes. Before we look at temperature and thermal energy, let's take a moment to look at the term heat. While the term heat is often used as a noun, it's actually a verb. Heat describes the process of transferring thermal energy. It's the flow of energy due to a temperature difference. For instance, if we put two blocks of metal next to each other that are different in temperature, here block A has a higher temperature than block B, when they come into contact, thermal energy will flow from block A to block B through the process of heating. This will continue until we've reached thermal equilibrium, meaning both blocks have reached the same temperature. Whenever objects of different temperatures come into contact with each other, the process of heating allows thermal energy to be transferred from the hotter object to the cooler object until thermal equilibrium is achieved. So in this class, instead of the term heat as a noun, we're going to use the term thermal energy. Thermal energy is transferred via contact. When two particles collide, energy is transferred from one particle to the other. Eventually, a thermal equilibrium is established. One way to quantify thermal energy is by measuring the temperature of a substance. The Kelvin temperature of a system is directly proportional to the average kinetic energy of the particles in that system. It's important to note here that this is an average. Therefore, not all particles will have the same kinetic energy. Recall that kinetic energy depends on mass and speed. Let's assume for simplicity's sake that all of our particles in our sample have the same mass. Therefore, the speed of every particle will not be identical. However, on average, they will have the same speed or the same kinetic energy. This means that some particles have a very low kinetic energy and some particles have a very high kinetic energy, while most particles have a kinetic energy somewhere in the middle of the sample. As temperature increases, the spread of kinetic energies increases, as shown in this Maxwell-Boltzmann distribution here. On this graph, the y-axis represents the number of molecules with a given kinetic energy. Notice the red line represents a cool sample. This is 0 degrees Celsius. At 0 degrees Celsius, notice that most of our particles have a kinetic energy in this region here, while some have less kinetic energy and some have more. As we increase the temperature, notice that our distribution begins to flatten out a bit now that we have more available kinetic energies. Still, most of our particles have a kinetic energy somewhere in this middle region, and a few have less and a few have more. Likewise for 2000 degrees Celsius, where an even wider distribution of energies is seen. So how do temperature and thermal energy differ? Temperature, as we've said, is the average kinetic energy. Therefore, it depends on the speed of the particles only, assuming all of our particles are of the same material, so they have the same mass. So it's only the speed that matters, not how many particles there are. Since it's an average, it's only the speed that counts, not how many particles there are. Thermal energy, on the other hand, depends on the speed of the particles and the number of particles. So larger samples of a substance at the same temperature will have more thermal energy. You can think of thermal energy as the total kinetic energy as opposed to the average kinetic energy. Take this example of chocolate milk. Looking first at glasses A and B, notice they're both 250 grams of chocolate milk, meaning we have the same number of particles. However, glass A is at a lower temperature than glass B, 5 degrees versus 70 degrees. Therefore, glass A has a lower temperature, or average kinetic energy. It also has a lower thermal energy, or lower total kinetic energy. Now comparing C and D, we see that we have much more chocolate milk here, 900 grams, as opposed to 250. However, both samples are at the same temperature. Therefore, the particles in C and D are traveling with the same average speed. However, there are more particles in sample D, therefore, D contains more total kinetic energy, or more thermal energy. As you likely already know, the first law of thermodynamics tells us that energy is conserved. meaning if energy is lost from an object, it must be gained by another object. Often we refer to these objects as the system and the surroundings. The system is the part of the universe on which we choose to focus. In other words, it's the thing we're studying. We can have open systems. Open systems are able to exchange matter and energy with the surroundings. Or we can have closed systems that can exchange energy but not matter. And finally, we can have isolated systems, which can exchange neither matter nor energy with the surroundings. This is really difficult to accomplish, so we'll only be looking at open and closed systems in this class. The surroundings, on the other hand, is everything else in the universe. Notice that this is based on a choice, so it's somewhat arbitrary. Consider this system and surroundings here. We could define the system as the green liquid in the flask, making everything else the surroundings, the flask, the box, everything surrounding the green liquid. On the other hand, we might consider the green liquid and the flask the system, making just the box the surroundings. When energy is transferred between the system and the surroundings, we can label these processes as endothermic or exothermic. An exothermic process is a process in which energy flows out of the system, from the system to the surroundings. This is easy to remember because exo sounds like exit. Energy is exiting the system. Therefore, energy is a product in a chemical reaction. It is produced by the reaction. An endothermic reaction, on the other hand, is when energy flows into the system from the surroundings. Again, this is easy to remember because endo sounds like enter. Energy is entering the system. In this case, in a chemical reaction, energy would be written as a reactant. For chemical reactions, these energy changes are the result of the difference between the energy required to break the bonds in the reactants and the energy released when new bonds are formed in the products. If it takes more energy to break reactant bonds than is released when new bonds form, then the reaction will be endothermic. On the other hand, if more energy is released by the product formation than it took to break reactant bonds, the reaction will be exothermic. We'll look at this in more detail later in this course. Here's a pictorial representation of what we just discussed. Here, the system is represented in yellow and the surroundings in blue. When energy transfers from the system to the surroundings, we have an exothermic process. This means that our energy change for the process will be negative because energy has been lost. On the other hand, when energy flows from the surroundings to the system, we have an endothermic process. Here, the delta E, or the change in energy, will be positive because energy has been gained. That brings us to the end of this video. Let's review our goals. First, we looked at the difference between temperature and thermal energy. Then we learned to differentiate between system and surroundings. And finally, we learned to differentiate between endothermic and exothermic processes.